Welcome, friends. Very good morning. Let me uh, let me stick to the presentation. Yes. So we have started with the slope stability, and we have discussed last time various type of slopes, especially infinite slope and the finite slopes. And in the infinite slope, we have taken the two cases. First is for cohesionless soil, and second is for cohesive soil. For the cohesionless soil, we have derived the equation and we have established that the slope angle I is very important parameter. If my slope angle is less than the value of internal friction, then my slope is going to be a stable. And if it crosses the value of phi internal friction, then probably the slope is become unstable. As well as we have taken several cases for cohesionless soil, like under submergent conditions or under saturated condition, what will be the difference in infinite slope equation will take place. Today, we are going to see one more case, same infinite slope, how it behaves under cohesive soil. So if you see, the dA, which is this, is the strength envelope, which is defined by our strength equation, shear strength equation, which is tau F is equal to C plus sigma tan phi. So if you see this strength envelope, so basically this will give you this angle with respect to horizontal will give you the value of angle of internal friction for the soil, and when it touches to the y-axis or shear stress axis, it will give the value of cohesion C, and that's how this equation has been actually formed. Now, if the slope angle is equal or less than a phi, which has been represented by line OB, which is this, right? So this is, I'm supposed to take angle I, which is less than, so suppose my slope angle I'm considering, which is I, which is less than the angle of internal friction. Then in that case, if you plot it like a OB line, which possess a similar condition, then you can say that there is no critical state of stress is reached and the slope is going to be stable, because if you see all the points which is well below your strength line. Now let us go further. If you draw a line OF which has an angle I, which is somewhat this, which is greater than the value of phi, you can see this angle is greater than the value of this. So line OF, right? Where it is? This, sorry, this is the OF. Yeah, this is the line OF, which is having an angle which is greater than the value of I. So it will cut the strength envelope at some point F, which is here, you can see. And the state of incipient failure is reached because the shear stress corresponding to the depth by point F equal to the shear strength tau F. So at the point F, your value of shear stress, which becomes equivalent to the value of tau F, right? However, at other point in the same line, still my value of tau is less than the value of tau F in this case. So basically, when I'm considering this equation, the variable is this value of sigma, and the sigma is depending upon the value of depth, since gamma into z, so the z is variable. So basically, as my value of z is increasing, my value of sigma is going to be changed, and depending upon that, as the value of sigma is going to be changed, my tau f value is also going to be changed with the value of depth. So that is how this strength envelope or the stability is also dependent upon those parameters. For depth z less than represented by point F, the shear strength tau is less than the shear strength tau F. And in that case, the slope is become stable. For example, the depth z corresponding to point C1 is stable for the slope angle even for the I greater than the value of internal friction phi. Hence, if I is critical then the phi, then the slope is stable only up to certain depth. Means up to certain depth of the slope, it is going to be a stable. Once you increase the value of slope, or rather increase the depth of the slope, in that case, when it is approaches to the value of F, you can see this value of F. So only variable is the depth. In that case, the slope is reaching to the critical state, and that height, when it is actually reaching to the you can say that stage when the slope is in the verge of failure, that particular depth which I'm denoting as critical depth, and its notation is HC. Now let's go further. So the factor of safety against the failure for any depth Z corresponding to point C1 of the slope when I is greater than equal to phi, greater than not equal to, right, rather I will say it is more than the value of phi. Let's see how it forms. So the factor of safety F is equal to, as you know, tau F upon tau. So tau F, we can put this equation C plus sigma tan phi upon the tau, where the sigma you already calculated last time, which is nothing but the gamma Z cos square I. There is some problem. This is not capital I. It should be the small I, which is slope angle. Please do the corrections. And tau is equal to gamma Z cos I into sin I. This equation we have already developed in the last lecture. So if you put those equations into this equation, then this value of F, which is a factor of safety, which will become C plus gamma Z cos square I plus tan phi upon gamma Z cos I into sin I. If you simplify those equations, then this equation which forms this particular form. Let's go further. Note that since non-cohesive soil is there, cohesionless soil is there, so this, if you put the C is equal to 0, then those equation will actually forms the previous equation what we have seen in the case of cohesionless soil. Very simple. However, we are discussing the case of cohesive soil. So for the critical depth, where we have assumed Z is equal to HC when the critical state of slope is reached, then corresponding to the point F, at this point, the tau F is becomes tau. So means at this particular depth or at this particular critical depth, the slope is in the verge of failure. In this case, I can consider the value of tau is equal to tau F. So if you put the factor of safety in this case is equal to 1, then the previous equation, which is this, here I am putting the value of F is equal to 1. So this will become gamma HC cos I into sin I is equal to C plus gamma HC cos square I into tan I. If I take the value of HC, then equation will be C upon gamma upon 1 upon tan I tan phi into cos square I. So if you see, here is the variable which is the slope angle I as well as the cohesion C and the gamma, which is the density of soil. Now let's see further. So this indicates for the given value of slope angle I and the internal friction phi, the critical height is proportional to the cohesion value. So if you take this parameters on the left side, which is C upon gamma HC, then the remaining content, which is tan I minus tan phi into cos square I, which is the constant parameter, which is which you can actually find out from the physical as well as the experimental values. So I is the slope angle, phi you can determine from the experiments. So these are the constant values. Then this I am supposed to say this is the dimensionless quantity, and this I am denoting as one more you can see the notation, which is called as the stability number. And the notation I'm going to give for this value, which is S suffix small n, which is stability number. So the Sn will become C upon gamma into Hc. Now let us take Fc, which is represents the factor of safety with respect to cohesion, and let Cm will be mobilized cohesion at any depth h, which has been given by Cm, which is the mobilized cohesion after the failure when the slope is in the verge of failure. So that is nothing but the Cm is equal to C upon Fc, right? So if you put this into those equation, then the Sn, which we have said it is C upon gamma Hc, if you put the value, replace the value of Cm, then this will become Cm upon gamma H. So this is, if you simplify those equation, then this will become C upon Fc into gamma H, because you have already used this particular equation. I'm using this equation, then this equation will form this is equal to 10I minus 10 phi into cos square I. If you plot this particular equation in terms of the critical height of the slope, then Fc, which is the factor of safety with respect to cohesion, this is nothing but the critical height of the slope upon the total height of the slope. So this way also you can calculate the factor of safety. The factor of safety Fc is with respect to cohesion, and also it represents the factor of safety with respect to the height of the slope. It is based on the assumption that the frictional resistance of the soil is fully developed. However, the true factor of safety is different from the value of Fc and is equally applied to both cohesion and frictional resistance of the soil. I hope this is very, very simple. In this particular theory, we have established the value of stability number, as well as we have seen the value of stability is also dependent upon the critical height of the slope, and as well as you can say C upon gamma Hc factor, right? Now let us take the same case with the submergence. If the slope is submerged, the gamma, that is the bulk density of soil, which is to be replaced with submerged density of the slope. Also, the value of C and phi is also to be determined corresponding to the submerged conditions of the soil. Means this value will be the effective value of cohesion as well as the angle of internal friction. So if you take the original equation of F and if you replace this value of gamma, then this value, which will tends to C plus gamma dash Z cos square I into 10 phi. Similarly, gamma dash Z cos I into phi I. So this equation will reduce to, we have already found out this equation. So this equation will reduce to this, and if you simplify this, you will get this particular equation. Now, in the case of steady seepage along the slope, if the water is seeping through the soil, again, the pore water pressure will comes into the consideration, as we have seen in the case of cohesionless soil. As the case of non-cohesive soil, the shear stress tau should be taken with respect to saturated weight, while sigma is also should be computed with respect to submerged weight. And then this particular equation, which is replaced in this way, because your gamma value, which is becomes a gamma saturated, and the remaining value, if you find it out, gamma saturated minus gamma W, then this value will reduce to submergence. So this value will become C plus gamma dash Z cos square I into 10 phi upon this particular value. If you simplify this, then you will get this particular equation. Now the critical height Z is equal to Hc, and as you know, since when this critical height is reached, then the slope is in the limiting condition of a failure, means it is in the verge of failure. In that case, I can put up my factor of safety value is equal to 1. Then this equation will reduce to, if I put the F is equal to 1 in this particular equation, then this equation becomes gamma saturated, height is replaced with the HC, cos I into sin I is equal to C plus gamma dash HC cos square I into tan phi. So if you find out the value of critical height of the slope, which will be C upon gamma saturated tan I minus gamma dash into tan phi cos square I, where I will actually stress upon it, whenever you will have the value of C and phi, you are going to use the value of C and phi, which is the effective parameters, not the total stress parameter. Here you are going to use the effective stress parameters. Comparing with these equations, it can see the effect of shearing resistance is being reduced, and which has been comparable with the previous equation what we have actually found out in 23.8. So this way you can derive the equation for cohesive soil as well for infinite slope. Now let us take one example of this type of formula, or this whatever the theory we have learned. So like this formula, this particular example says a long natural slope of cohesionless soil is inclined at an angle of 12 degree to the horizontal, taking the value of internal friction phi is equal to 30 degree. Determine the factor of safety of the slope. If the slope is completely submerged, what will be the changes in the factor of safety? So basically in this particular example, you have been given, this is a cohesionless soil case, number one. Second, the slope is been inclined to 12 degree with the horizontal. There is no height of the slope is been given, so you can assume this is the infinite slope case. Value of phi is given, which is 30 degree. You need to find out the value of factor of safety if the slope is completely submerged case. So you need to take the case of submergence. So if I use this formula, this is nothing but F is equal to tau C upon tau plus tan phi upon tan I. Value of phi is given, I is given. You can put this value, you will get the value of factor of safety. Now, if you put the value of submergence case, when the slope is become submerged, the gamma is going to be replaced with the gamma dash. Then the F is equal to gamma z cos square I tan phi gamma z sin I upon cos I. This equation we have already developed. So from this, if you put the value, then you will get the value of submergence, which is 2.72. So you can see this value and this value which remain same, right? Okay, let's take one more example. A long natural slope, so it is an infinite slope of sandy soil where my phi is equal to 25 degree and the slope angle, it is inclined at 10 degree to the horizontal. Water table is at the surface and the seepage is parallel to the slope. If saturated unit weight of the soil is 19.5 kilonewton per meter cube, determine the factor of safety of the slope. So in this case, again, let us take few things. One is, it is a long natural slope, means it is an infinite slope case.